Video, we're going to look at understanding the matrix and addition and subtraction. So we have four different matrices, A, B, C, and D, and we have certain rules for combining these things. So if I look at A and B, A is a 2 by 3 and B is a 3 by 2. So again, we have two rows, so 2 rows by 3 columns. And B is a 3 row by 2 columns. And they cannot be combined. So you can only do like rows and like columns and combine them in addition and subtraction. So A, C, and D can be combined using addition or subtraction. B, on the other hand, cannot. B is the odd man out. He is the one not like the others. Right? But let's look at things. Let's look at deeper into combining what these matrices look like if we combine certain matrices. So let's say I'm going to combine A and D. And what I find with A and D is they are the same values but opposite signs. So if I'm doing A plus D, I'm going to do 5 minus 5, because 5 plus negative 5 is 5 minus 5. 4 plus negative 4, or 4 minus 4. Negative 7 plus 7. 8 plus negative 8, or 8 minus 8. 3 plus negative 3, like how I wrote that out instead of 3 minus 3. And negative 2 plus 2. So what I get here is when I do all this subtraction, I get a 0 for 1, 1. I get a 0 for 1, 2. I get a 0 for 1, 3. I get a 0 for 2, 1. I get a 0 for 2, 2. And I get a 0 for 2, 3. And eventually, we get a matrix with all zeros. When the sum of the two matrices is a zero matrix, the matrices are additive inverses. Again, we've talked about inverses, and they are the opposite. So the 0, 2 by 3 matrix is a or a 0, 3 by 2 matrix would also have all zeros, but would have 3 rows and 2 columns. So we're still looking at these zero matrices. And again, they are additive inverses. So let me write that out. 0 matrix is the matrices are additive inverse. Or again, they undo each other. They become 0. We've talked about inverses undoing the function. Basically, A undoes D and D undoes A, and we get 0. We get a null point. All right. So what is an additive inverse of matrix B? So looking at matrix B here is a 3 by 2. And my additive inverse would be something that I would add to it to make it 0. So I'd have B plus X. And when I add those would be equal to 0. 1, 2. Which means that B plus X would equal 6, 5, negative 2, 0, 3, negative 4. The values here that would make this first row, this 1, 1, 0, would be a negative 6. The thing that would make the 1, 2 a 0 is negative 5. The value that would make a 2, 1 a 0, that's a lot of numbers. Row 2, column 1, the value of 0 would be a 2. This is 0, so 0 plus 0 would be 0. I forgot to put a plus in there. 3, it would be negative 3 and 4. So in our case, x, our value x, our variable x, would equal the matrix negative 6, negative 5, 2, 0, negative 3, and negative 4. This value of x is our additive inverse. Add. So that is our additive inverse. The additive inverse is a matrix, the additive inverse of a matrix is a scalar multiple of negative 1 times the matrix. So I could now say that the additive matrix is a scalar of negative 1 times the matrix. So again, A would be negative 1 times A, and that would be the additive matrix. So how does A plus C relate to C plus A? Another thing to look at if we're multiplying a different way of matrix. So A plus C, I'm choosing colors. A plus C would be 5 plus 12, 0 plus 4, negative 7 plus 0, 8 plus 15, 3 minus 3, negative 2 plus 2. So then A plus C would equal, oh, what did I get? I jumped, hold on, I jumped here. I went to D and I didn't stay with C here. This is 15, this is 0 and 9. I was like, wow, those are just zeros. But I jumped all the way down. My eyes went down too far. 0 and negative 2 minus 9. All right, so this would equal 17, negative 7, 3, 4, 23, and negative 11. And what if I did the I could never say that. The cumulative property, and I did C plus A. Do we get the same thing? Well, when I add them, I still get 17 and negative 7 and 3, 4, 23, and negative 11. So I can now say that A plus C is equal to C plus A. And the matrix addition is real number addition of corresponding elements. So I can never say it. C-O-M-M-U-T-A-T-I-V-E, commutative. Basically, it's this property. I'll spell it out. C-O-M-M-U-T-A-T-I-V-E. Property exists, and this additional thing still holds. All right, guys, sorry for the mix-up on the numbers and not being able to say commutative. I don't know why that's so hard for me to say, but it is. But there you have it. Just different scenarios using a matrix. There's nothing very deep or in-depth about this. We are still at the very beginning stages of matrices, so we're not diving quite as deep into this in this example. But we will start looking at different examples that dive a little bit deeper. All right, if you have any comments or questions, always feel free to ask, and I will catch you in the next video.